Afternoon, ladies and gentlemen. My name is Andrea Zappettini from the Italian National Research Council, and actually I am chairing the Commission for Crystal Growth and Characterization of Material of the International Union of Crystallography. This evening I am the honor to be here to chair this keynote lecture session, and our keynote lecturers this evening will be Professor Jim de Yoreo, and de Yoreo is actually professor of chemistry, material science, and engineering at the Washington University, and he's also chief scientist at the Pacific Northwest National Lab. And I, of course, want to tell you that the scientific curriculum of Professor de Yoreo is really amazing. He published on the most important international journals in the world. And also, he has been awarded by many national and international institutions. And in particular, I like to remember when he gave an amazing lectures when he received the Lodis Prize, that is the main award that is given by the International Organization for Crystal Growth. And really, the work of Professor de Yoreo concerned the study of the physics of at the nanoscale of interaction at the solid-liquid interface, and interaction and assembly. And this is both for inorganic and organic crystals. And he can do that by using in situ scanned probe microscopy typically, and in situ transmission electron microscopy, together with a lot of also theoretical work. I'm very happy that Professor de Yoreo accepted the invitation of the organizer here, because actually he will talk to us about something that concerns crystal growth, and I think that hardly there could be crystallography if we are not able to grow crystals, and so it's very important for a conference on crystallography to talk about crystal growth, and also because Professor de Yoreo will talk to us about nucleation, which is really the beginning of crystallization and crystal growth processes. And all his work is done typically with techniques that I really have much to do with crystallography. So, Professor de Yoreo, thanks for coming, and please give us your keynote lecture.
So let me start by thanking Andreas for that generous introduction, and also the organizers for inviting me to speak here today on our work on nucleation and crystal growth. So as you certainly all know at this conference, crystal growth is a pervasive phenomenon, not just in technological settings, but also in the environment, both in geochemical reservoirs, in soils, and in the atmosphere, but also in biology on both the soft side, where materials like the outer membranes of bacteria and archaea crystallize into two-dimensional crystals, and in the case of organisms that make mineralized tissues, like this beautiful coccolithophorid that makes this wonderful array of calcite crystals. And of course, in our case, and as humans, the most important crystals in our body being our bones and our teeth. Now, all crystals start with nucleation, and the theory of nucleation goes back to the most famous of chemists, J.W. Gibbs, who proposed a theory of nucleation back in the 1870s. Now, Gibbs had in mind water droplets, but this theory was quickly taken over to be applied to crystals as well. And in the classical theory of nucleation, ions come together to form a nucleus. And of course, that happens because there's a drop in chemical potential, delta mu. And the total free energy due to that change in chemical potential is proportional to the number of ions that transfer from the solution to the solid state. And so it's proportional to volume. On the other hand, the creation of the nucleus leads to the formation of an interface between the solid and liquid, and there's an energy penalty to pay for making that, which we usually think of as a surface tension. Of course, it has to do with the unsatisfied bonds on the outside of the solid that then interact with the solution. And because that contribution to the free energy depends on the number of surface atoms. It's proportional to area. The consequence is that we add together a negative free energy term that goes cubically with the size of the nucleus, with a positive free energy term that goes quadratically with the size of the nucleus. And when those are added together, of course, they form a barrier because the quadratic wins out at small size and the cubic wins out at large size. Now, because there's a free energy barrier, we can write the rate of nucleation as being proportional to two Boltzmann factors. One of them, this one that's exponential in the E sub A, an activation barrier, just has to do with atomistic processes like ions desolvating from the solution or attaching or rearranging. But the second Boltzmann factor has to do with this collective piece of the problem, that is, the search for all the possible configurations that leads to this free energy barrier. And that free energy barrier depends on these two parameters that show up in this free energy change here, one being the chemical potential change, which we can affect by changing things like concentration and temperature, and the other one, which we don't have control of largely, and that's the interfacial free energy. And I want you to note that the interfacial free energy is a cube inside this barrier. And so when you put a cubic term into an exponential, it has a huge impact on nucleation rates. Now, I want to show you that this theory of Gibbs in principle works in describing nucleation as an overcoming of a free energy barrier. The only way you can get over a free energy barrier is through fluctuations, and at finite temperature there are always fluctuations in the solution that create regions of higher density and lower density, and some of those eventually overcome the free energy barrier. Now, you'll see that happening in this movie. Nucleation occurs in many places, but there are some that don't make it, and I've highlighted one of them here, and I want you to pay attention to that one. Here you can see the nucleus appearing, but you notice how it's fluctuating in size. It gets bigger and smaller and bigger and smaller, and eventually you'll see that it just disappears. It gives up the ghost. Well, since about maybe the past 15 to 20 years, we've come to realize that this picture of nucleation is only partially correct, that there are other pathways that were not envisioned in the simple classical nucleation theory. And they come, these other so-called non-classical or hierarchical pathways have come in four varieties, each of which I want to talk about briefly. The first one is one in which the pathway to nucleation involves chemical reactions. In the case of calcium phosphates, for example, there's a minority species in solution. That unit can be essentially found in the final crystal. But it doesn't assemble to make that crystal. It first assembles into a polymeric structure, which then undergoes a chemical reaction through the addition of calcium and the loss of protons to form an amorphous material, which again, through the addition of calcium and the loss of protons, becomes the first crystalline phase, octocalcium phosphate. The second example is one in which there's a special size in the system. This is an example of some quantum dots, made indium phosphide quantum dots. And in this case, what the researchers observe is that starting with the precursors, there's an intermediate state of a special size. They see no sign of anything in between and no sign of anything between this special size and the final quantum dots in the system. And so it apparently represents an intermediate low energy state of the indium phosphide particles. The third example is one in which there are clusters in solution that are actually quite large. Now, I should say that this is a somewhat controversial case for the particular example here shown, which is calcium carbonate, though it's surely known to be the case in iron oxide systems and in silicates. And that is that large clusters form in solution. And even in undersaturated conditions, there's a stable population of these large dynamic clusters. And they aggregate to form an amorphous solid. And then through a process that's not well identified, although I will talk about it, that amorphous solid then turns into nucleates the crystal. And the final example is one in which the system doesn't even make a solid to begin with, but it makes a liquid. Now, spinodal decomposition is not exactly non-classical, but the case that I'm speaking of is slightly different. And that is that unlike a spinodal where the liquid state is lower in free energy than the solution itself, that is the phase-separated state is lower in free energy, The phase-separated state is a metastable state higher in free energy, and so it also can only exist in microscopic levels and only can form through fluctuations, but it's the necessary precursor to the final crystalline state. Now, I want to add to this the observation from the world of biomineralization that in living systems, there are other components introduced into the system to direct the pathway and decide what phase will appear and when. And there are two important components. The first one is, I'm going to show you two examples here. In both cases, you'll see that the material that is formed, although it's crystalline in the end, it starts out as amorphous phase, in this case amorphous calcium carbonate. And this process of amorphous phase formation and transformation is regulated by ions and macromolecules. In the case of this land crustacean, which as a child we called roly-polies, the shell of the molting land crustacean, as you can see from the SEM images here, is made of, TM images here, is made of amorphous nanoparticles. And you can see from the diffraction pattern that they're amorphous. And over time, and they contain a high content of magnesium. And over time, aspartic acid-rich proteins are upregulated in the system, and this turns into calcite. But of course, the shell maintains its shape the entire way. And so through this process, it's able to do an isomorphic transformation of the shell from amorphous to crystalline. The other example, which is actually quite widespread across different types of organisms, is represented here in the mollusk, in this case abalone. Abalone has this beautiful shell because the nacre layer is composed of these platelets of calcium carbonate, here in the form of aragonite, another polymorph of calcium carbonate. Each of those platelets is separated by a proteinaceous sheet, and the platelets are connected together so that they're all co-aligned as a single crystal to form this so-called stack of coins. What Hooper-Gilbert's group showed that is if you analyze the growing tip, what you find is that it starts out as amorphous material, amorphous nanoparticles, which then transform to the aragonite phase as it ages. And what the Adati group showed is that in addition to this, if one looks at these sheets, near the center of each platelet, there's a sulfate-rich region, and in the center of that, there's a carboxyl-rich group that apparently has some role in controlling the nucleation, either of the amorphous phase or its crystallization to the aragonitic phase. Okay, so why is this such a complicated problem? I talked already about the simple description from Gibbs, but the answer is because the world's more complicated than that, and it's complicated for two reasons. The first one is because there are complexities in the free energy landscape. Instead of having a flat landscape where it's always uphill until you reach the critical size, let me jump over to the right-hand side here. It can be more complicated because there can be other phases in the system that represent bulk phases on a phase diagram, and they may be metastable relative to the solid, but they're stable relative to the liquid, and they may be easier to make for kinetic reasons or because the free energy barrier is lower due to a lower interfacial free energy. And the consequence is that the system may make that metastable phase first. But the second reason is because there may be phases that are locally metastable relative to their neighbors because they represent special configurations, or they are at special sizes such that the coordination of water around the surface is more favorable, but they're not even stable relative to the solution, and so they can never exist in bulk quantities, but they may be microscopic states that are passed through on the way to the final state. But it can be more complicated for dynamic reasons as well, that is because of kinetics. And so, for example, if the system is driven to very high supersaturation, I may make many, many nuclei that even though they may be smaller than the critical size, they can still interact to grow to crystals in a hierarchical fashion. But of course, the system in the end would like to be one single crystal separated from the solution. And even in the case where we make metastable phases, the system may get stuck into these non-equilibrium states because the atoms or molecules simply don't have the mobility that it takes to reorganize. Now, the answer to this is really quite simple, is that we could write all of the same change in free energy. That certainly that expression is not incorrect. But what's incorrect is to simply write a constant interfacial free energy that's given by the bulk surface tension. And that's where the problem lies. It's more complicated. We have to write this as an excess free energy, and it can depend on many factors, and can even involve chemical reactions. So the question that we're left with is, we know that complex pathways can arise for both thermodynamic or kinetic reasons, but the question is, in real systems, in which ones do they occur and for what reason? So we're going to look at this today in a couple of ways. And the first couple examples I'm going to show you is going to use in situ TEM. The movie of gold nucleation that I showed you was in situ TEM. And right now I'm going to talk about the work of Mike Nielsen. This is a holder that we've used for investigating nucleation. It's a nice technique because it allows us to mix reagents. Those reagents mix right at the entrance to a sealed fluid cell. It's vacuum sealed so that it can go into the TEM. And then there are two thin membranes where the electron beam passes through that are silicon nitride in composition. And there's a little pocket of solution here. Most of the fluid flows around this, but some component of it flows through the middle of the cell. And then we can watch the process of nucleation and growth. Okay, so first I want to look at this case, the case in which we have a metastable phase. In this case, it's going to be the combination of a high chemical potential of the solution and the existence of multiple phases that will lead to these hierarchical pathways for thermodynamic reasons. And this is the case of calcium carbonate. And what we see in our in situ TM experiments that Mike did is over a wide range of composition, we can achieve all of the phases of the system. Amorphous calcium carbonate, or ACC, aragonite, vaterite, two forms of vaterite appear, and calcite. And this is ex situ images and diffraction patterns in some cases. And these are the in situ images. That's all right. Showing you, in most cases, we can obtain the diffraction patterns as well. It turns out when we look at the growth in these cells, for the most part, we have a relatively linear dependence of growth on time that is a constant growth rate, which is an indication that we are surface kinetic limited and not mass transport limited, which would give us a square root dependence. There are some exceptions where we see a change in slope, and we assume the reason for that is that some crystal forms near the inlet to the cell, and then it reduces the supersaturation at the site of the growing crystal that we are imaging. Okay, so let me show you two different kinds of pathways that we observe in this system. On the left-hand side is an example of a direct pathway of nucleation. This is calcite. But in this case, two separate phases appear in the same experiment. And so this shows you that this case that you can have multiple phases in a system, and they even impinge upon one another and continue to grow. The second example on the right is one in which we have an indirect pathway via a precursor. Now I want you to note this region, this line here is the separation between the electron transparent region of the cell and the thicker portion of the cell where the electrons they have a high mass density. The cell has a high mass density, and so it's darker. This is not inside the cell. This is a deposit on the outside of the cell that Mike simply used for his focusing. And now what you see in this particular movie is, here's the start. Now this turns out to be amorphous. This is amorphous calcium carbonate, or ACC. But at some point it realizes it wants to have a little more structure in its life. And you'll see right on the surface, in two locations, the appearance of aragonite, there and there. And it transforms into the second phase. Now, this is one of the beauties about in situ microscopy, right? We would have no idea that this process took place if we weren't looking at it in real time. So what Mike showed in well over 100 TEM experiments is that, as I said, he could find all phases. He could see examples where the amorphous phase transformed into either a vaterite or aragonite, and he documented at least one case where aragonite transformed into calcite. Although we never saw any pathway to calcite other than direct nucleation. But of course, that doesn't mean it doesn't happen. We only did, of order. Pardon me? Play the movie again. Oh, okay, sure. I can do that. I hope. No problem. There you go. I want you to notice that when this occurs, the nucleation is right near the surface of it. And that's what we always observed in these experiments. Okay? Okay, so why does this happen? Is this non-classical? The answer is no. It's not non-classical. If you look at the, is this readable to you? I'm sorry, you can't see the scale, and that's important. Let me fix this. Okay. Even that's probably not good enough, but we'll live with it. So this is the free energy barrier in units of kT. Okay, so anything that's much bigger than kT is very unlikely to happen. And versus the length of a calcite crystal. And this range of supersaturation, sigma, which is just delta mu over kT, are the values typically used in the laboratory for calcite experiments. It doesn't matter what those numbers mean. I just want you to know that they're usually the range of values that are usually used. Because if you go lower than that, nothing happens. And this is the solubility limit of the amorphous phase in the literature, though many of us believe that it's somewhat lower than this. And what you see is that even when you cross the solubility limit of the amorphous phase, the barrier to making calcite is still 100 kT. And so it's a very difficult crystal to nucleate. Now, imagine if I raise the concentration of the solution up until it's supersaturated relative to the amorphous phase. Well, now I'm supersaturated with respect to all phases. So which one's going to form? The answer is all of them, in some proportion. And those proportions are given by the ratio of these Boltzmann's factors, right? Now, I may be able to calculate the free energy barrier, because it goes like alpha cubed over sigma squared, and I know all the parameters in here. But the problem is that when the supersaturation gets very high, of course, this term can become negligible compared to these activation barriers associated with atomistic processes. And of course, we don't know what those processes are. We don't even know what the units are that come together to form a calcium carbonate nucleus. And so it's a hopeless problem to try and predict which phase is going to form. All right, now let's change this a little bit. We're going to add in some macromolecules that are surrogates for the sulfate-rich macromolecules in mollusks and other organisms like Coccolus. And we're going to see how that freezes the system into a non-equilibrium state. And this work was done by Paul Smeets, a student of mine and Nico Sommerdijk's. And here, what we show is that the addition of highly charged polymers that bind calcium creates a state that's called the globular state. He used a polymer called polystyrene sulfonate, which you can just think of as a chain of sulfate groups, charged sulfate groups. And in a calcium-free solution of polystyrene sulfonate, there's nothing to see in the TEM because the polymers are all loose chains. They have no problem having their functional groups extended. They don't want to collapse because all those functional groups are charged and they repel one another. However, when we add calcium into the solution, the calcium binds to the sulfate groups and the polymer chains collapse. And they collapse into, and because they're divalent cations, they can link together polymer chains and make what's called a globular state. And so you can see these diffuse-looking, low-density, low-contrast blobs. And they're of order about less than 50 nanometers in diameter. But I should mention that the cell thickness is only about 50 nanometers. And in fact, if we look at these in dynamic light scattering, they're really more about 20 nanometers in diameter as spheres. But they're adsorbed onto the silicon nitride membrane. Now we know that the calcium is binding to the PSS because we did zeta potential measurements. And you can see the negative charge of the polymer. But as you add calcium, it shifts upward towards more positive values. We also know that the calcium binds to the sulfate because if we look at the infrared spectrum, we can see the sulfate stretch without calcium shift when we add the calcium. Paul also did titration calorimetry and showed that about 56% of the calcium in solution is now inside of these globules. Okay, so more than half of it goes into the globules. Not surprisingly, now when we add carbonate into the system, nucleation happens inside the globules and nowhere else. Okay? And now if we look at what is that solid inside the globules, what we find is it's amorphous. But if we leave it under the beam too long, it crystallizes into calcite, and that's how we know, in fact, that it's calcium carbonate. If we don't do that, it remains amorphous for the length of the experiments. Now, one of the valuable aspects of these in situ experiments is we can record the nucleation event and the rate at which these nuclei then grow. This is the nucleus within a globule. I should say that it's hard to focus on both the solid material and the soft material because for those of you who know TEM, right, you need different defocus values in order to put those two into focus. So it's a little bit tricky. Because we can measure growth rates, we can then analyze the data in the presence of polystyrene sulfonate where we make ACC, and without the polystyrene sulfonate where we make vaterite or calcite. Here you can see vaterite forming, and plot those growth rates versus size. And then by fitting this data, we can get the initial growth rate, and from that, the supersaturation at the time of nucleation. And what we find is that in the absence of polystyrene sulfonate, well, the supersaturation relative to vaterite is about 0.5 to 0.6, okay? And in and of itself, that number means nothing. But what we find when we analyze the formation of ACC in the presence of polystyrene sulfonate is that the supersaturation that the system has to get to before the ACC will form is more than twice that value. And remember, that goes into an exponential. And so the system is actually being driven much higher in chemical potential, and the barrier to nucleation is larger. So polystyrene sulfonate does not promote nucleation of ACC. First of all, it inhibits the nucleation of anything else because it sucks up all the calcium. But in addition to that, when nucleation occurs, the amorphous phase forms and it can't get out of the amorphous phase because of the polymer. Well, we don't know exactly what the mechanism is there, but the polymer presumably limits the mobility of the ions, and the transformation to calcite or vaterite or aragonite no longer occurs. Okay, so now I want to show you the case of magnesium, which is quite interesting. This is the work of Xiaoming Liu. Here, I want to say, first of all, that the overwhelming majority of the time when amorphous calcium carbonate transforms to a crystalline phase, it happens through dissolution reprecipitation. But that's delayed when you add things like polyaspartic acid or citrate, which are common macromolecules and organic molecules in mineralizing systems, as well as low concentrations of magnesium. And you remember I told you that magnesium and carboxyl-rich proteins played an important role in biomineral formation. So this movie on the left shows you what happens in a typical experiment. This is amorphous calcium carbonate, and you can see the amorphous calcium carbonate growing here, and then all of a sudden you'll see it dissolve. Okay, and the reason why is, well, early on when we see this is what we get, that's amorphous. But if you search around the cell at the end, so when Xiaoming searches around the cell at the end of the experiment, what he finds inevitably is a crystal somewhere, vaterite or calcite, right? So we don't know for certain whether or not that particular crystal started as an independent nucleation event or a transformation of an amorphous particle. But once it forms, it drops the concentration of the solution and all the amorphous phase disappears. So simply by tracking the contrast, the mass density, the gray value of the image, we can look at the growth period, the stability period, and the dissolution period of the amorphous phase. And so here's a typical, a plot. So this is the ACC growing in, this is a period of relative stability, and this is it dissolving. And that means we can now compare additives. So I'm showing you three examples here for magnesium, citrate, and polyaspartic acid. And I've adjusted the numbers of the concentrations so that they not only give the concentration in the molarity or in the case of the macromolecule in mass per volume, but also in terms of the number of functional groups. So while this is 2.5 millimolar magnesium, there are 1.5 millimoles of carboxyl groups in this experiment, and about 6 millimoles of carboxyl groups per liter of carboxyl groups in this experiment. He did this for a number of concentrations. I'm just showing you one example. And what you see is, in the case of magnesium, a greatly extended period of stability. That doesn't mean that the amorphous phase is more stable, right? It means that the nucleation of a crystalline phase takes longer in the presence of magnesium. That's well known in the calcium carbonate system. On the other hand, it does very little to the dissolution rate of the ACC when it does occur. Citrate has no effect on the stability, but it slows the dissolution, and polyaspartic acid affects both periods. Okay, that's not very exciting, okay? So what? What's really interesting is if you increase the magnesium level to 5 millimolar, 5 millimolar or above, we get a completely different pathway. And I'll show you this movie. So you can see already these things look different. And what you see is rather low contrast objects that get darker as they grow. If we go to slightly higher concentrations, 7.5 millimolar, something similar happens. It just takes longer. So eventually you see them, they become darker and darker. They're floating around. Okay, so what's really surprising about this is that when we look at the diffraction patterns, they start out as amorphous, but at the end they're calcite, and they haven't changed their shape. They've undergone a pseudomorphic solid-state transformation into the calcite phase. And if we analyze the solid products by EDS, we find that, yes, indeed, the magnesium is still in there. So we've made mag calcite from magnesium-rich ACC. Now, if you look at an individual particle, what you find is that this is not a uniform increase in contrast. In fact, the solid nucleates within this particle and then spreads through it. And if we analyze the change in mass density just based on the relative contrast, well, we have to take out the effect of the increase in size. But once we've done that, you can see this transition. Now, it turns out if we do attenuated total reflection FTIR, what we find is, well, first of all, this peak, the new 2 peak, this is the typical peak for calcite. And you can see that with time, the calcite peak grows in. And I should note that the colors here are the same as the colors here. And the times here are in minutes. Okay, so this is from 1 to 18 minutes. But there are 2 other peaks here at large wave numbers that disappear in the first 5 minutes. Those are structural water peaks in minerals. And so what's happening here is that calcite is forming by the dehydration of these particles, which have structural water. Now, we also performed TGA on these and showed that, in fact, the addition of magnesium increases the amount of water. But more significantly, we performed molecular dynamics simulations and made hydrated magnesium ACC clusters, and then played a trick where this is the work of Jisen Zhang at Xiamen University in China. Jisen put in a barrier that only let water pass. And then the water would periodically pass through this and leave behind only the structural water in the clusters. And then he analyzed both the radial distribution functions, showed that with the water that there's a much broader peak due to the fact that the water coordinates with the carbonates and replaces the cation carbonate coordination, but it's much less stable. And that's reflected in the root mean square deviation of the positions of the ions in one of these ACC particles, where you see that as you add magnesium, the fluctuations become larger and larger. And so the magnesium is doing 2 things. On the one hand, it's inhibiting nucleation of independent crystals out away from the particles, giving the particles more time to transform, but simultaneously, it's destabilizing the particles. It's giving the ions more mobility. It's putting fluctuations into the system that allow it to find the nucleation point and transform into the crystal. And perhaps this is why so many biominerals have magnesium in them, because it allows the organism to define a shape initially by creating the amorphous calcium carbonate aggregate. Okay, so now I want to go to this, which is perhaps the most interesting part of this diagram, and that is where there are transient states that don't exist in the bulk. Now, I'm going to shift gears here and do experiments with AFM. AFM is nice because it gives us a molecular view of the world, but of course it only works on surfaces. But I'm going to show you here an example of the crystallization of bacterial membrane. It's an S-layer membrane, so it's made of S-layer, surface layer proteins. And you'll see 3 brightness levels here. The darkest area, well, that's the top of the substrate, which is a lipid bilayer. The brightest areas, like here and here, that's the beginnings of nucleation. And the rest of this is protein moving around on the surface. Well, you can see there goes nucleation. Once the domains form, it starts adding on new proteins. Those are actually tetramers that are adding on. And I want you to notice at the beginning that these are not crystalline to begin with. It's a little hard to see. That goes by pretty quickly. I should slow this down. I'll stop it at the beginning. All right, so you can see this is amorphous. You can start to see the crystallization taking place perhaps in this one. Here are 3 still images that show the initial point. These are proteins adsorbed on the lipids, so they're individual proteins. They're not folded into tetramers. This is the point at which we have the amorphous precursor. They only exist as nanoclusters. They never grow into a bulk phase, and then they transform into the crystalline state. The second example here is one in which we are able to change the system from a classical direct pathway to one that passes through transient state by taking a small organic molecule called a peptoid and adding on a hydrophobic tail. In both cases, they form this so this is crystallizing on mica. And what you're looking at here, these rows, these are actually vertical sheets. They're crystalline sheets standing up, and they're 1 molecule in width. Okay? And they align with the 3 equivalent directions of the cation lattice on the mica surface. And it's because these carboxyl groups, it turns out, have the right spacing to be epitaxially matched to the cation lattice. And once that happens, the second row, the hydrophobic groups, bury themselves together to make a bilayer. That exposes a new row of carboxyl groups. Calcium in the solution then binds to the carboxyl groups, and that starts this process all over again. And so you get vertical sheets. Now, if you look at the one without the hydrophobic tail, there's nothing very exciting here to see. This is nucleation. Grows into fibers. They're ordered right from the beginning. You can see that they grow in this bilayer fashion in 3 nanometer jumps, independent of the concentration we choose. There's a simple Langmuir dependence of particle number on time, because as you fill the surface up, it reduces the nucleation rate. If we look at the rate of nucleation versus 1 over sigma squared, remember the nucleation rate is exponential in alpha cubed over sigma squared, we get a nice quadratic dependence, and out of that we get an interfacial free energy, which is a completely reasonable number. Okay, that's the classical picture. When you add on the hydrophobic tail, it changes completely. So now this is the number density versus time. That surely does not look like a Langmuir dependence. It's nonlinear dependence increasing with time. And in fact, there's a region down here which is roughly linear, and then it becomes quadratic. Well, maybe it's quadratic to begin with, I can't really say. But then it becomes more rapid and linear. And if we go to low enough concentration, we lose the transition to this rapid regime. And instead, it just remains low and linear. And if we take one of these solutions and we filter it first, we also lose this transition. So that transition is due to something in solution that we don't know about on the surface. And in fact, if we look at the images, it turns out that one of the problems with AFM you have to be careful about is that what you see depends on the dynamic range that you choose. And so in the dynamic range that I showed you initially, you wouldn't see anything different than in the previous movie. But going to higher dynamic range, it turns out that the surface is covered with 2 other species. One of them are 3 nanometer high clusters. I'm sorry, the 3 nanometer high clusters are the ones that you see here. That's the bilayer, okay? And it looks like it's round here just because we've changed the dynamic range so much that it's off scale and you're imaging the shape of the tip. But in addition to that, there are the monomers on the surface, and there are these 5 angstrom high clusters. Now, if we track those, these are the 3 nanometer nuclei. That's the same as what I showed you over here. But along with these 3 nanometer nuclei, which grow in number and then make a transition and grow more rapidly, there are these clusters. And those clusters are growing more rapidly in number till just about the time when this transition occurs. And then they drop in number. And so they have something to do with nucleation. And in fact, if we track the percentage of the nuclei that come from the clusters, so the percentage of these that come from those, what we find is that early in the experiments, all of the nuclei in the system start out as these 5 angstrom high clusters. But at about the time of this transition, the percentage that are coming from clusters drops off. Where are the rest coming from? Directly from solution. And it turns out that what's happening here is that this system makes disordered clusters. They're probably micelles because they have a hydrophobic tail now. And these little micellar units are depositing onto the surface, undergoing a structural transformation into the nuclei, and then growing. But later in time, they're able to do that transformation in solution. The surface is just catalyzing that transformation. It would happen anyway. And the consequence of that is that nucleation is then dominated by the ones deposited from solution. So in this system, we have a simple description for the polymer without the tail. But we add the tail, we introduce this intermediate metastable state that can only exist as microscopic structures. Okay, so what does it take to get a complete and predictive model of nucleation? Well, what I've just shown you is that the landscape is complicated. And if you really wanted to know what it was, you would map out the cluster size distribution prior to nucleation. Okay? There's also this added problem of how to include chemical reaction networks. But I want to focus on this question. What's the cluster size distribution? It's a really hard problem. There's no technique that we have that can look at a bulk solution and look at the distribution of clusters at sub-nanometer length scales. Right? We can do scattering and get a broad peak that's an average, but how do we look at the cluster size distribution? Well, modern day, so let me just tell you what it should be. Okay, if you look at the classical picture, this is work from Ben Legg, a postdoc in my group. In the classical picture, the work of formation increases with number, with cluster size. And if I put that work of formation into an exponential, of course, the cluster concentration is dropping exponentially with cluster size, okay? It should drop, if I were to plot the log versus the number, this would be a line, okay? But I'm doing it versus cluster size, so it's got a cubic dependence. The consequence of that is that if you look at a nucleation simulation, right, clusters hardly ever make it to the state of nucleation. Here's one that's finally done it, okay? Nucleation is a rare event, and the clusters ought to fall off exponentially with size. So the question is that what one sees in the real world? So we're trying to do this with AFM, because these days AFM gives atomic resolution. Here's an example of potassium chloride in a solution on mica, and you can even see the potassium ions on the surface at 2 millimolar, where we have low coverage of potassium, and 150 millimolar, where the potassium coverage is 100%. Now, with resolution like that, we should be able to start to look at clusters. Now, the system that Ben chose is gibbsite, aluminum oxyhydroxide, on mica, because it grows epitaxially, and Paul Fenter's group showed that you can grow a layer of gibbsite on top of mica, and came up with somewhat of a model for this, a schematic model. So Ben has been looking at this, and in fact, this works. So this is the system at 1 millimolar aluminum chloride. I'm sorry, obviously there's a mistake here, and this is not aluminum carbide, it's aluminum chloride. 1 millimolar aluminum chloride at 30 degrees centigrade. At 10 millimolar HCl at 2.1, pH 2.1, you're below the solubility, and all we see are individual ions adsorbed on the surface. As we decrease the amount of HCl, we're going up in pH, and we're going to start crossing the solubility limit. You start to see the appearance of clusters, and they're dynamic. And as we go to higher pH, the number density of clusters grows. You know, looking at this by eye, you get the sense that there's a domination by a certain cluster size. Ben recently has been able to actually collect cluster statistics. So here's a nice movie. This is at 40 degrees, 26 seconds per frame. And by thresholding these images, he can then count the number of clusters per nanometer squared, versus their size. Here, he's plotted it versus area, angstrom squared. So this is the same as number. And so in the classical model, this ought to be a linear dependence. And it's pretty linear over most of the range, except right down at small size here, about 1 nanometer squared, which is about the size of a hexamer. And it's those clusters that stood out in the images are the ones that are making up a larger number density here. Unfortunately, of course, it's like everything in life, it's pushing us down at the limit of the instrumentation. But it looks like there may be a special size in the system, though this is preliminary at this point. Okay, so how does nucleation occur? So this is what happens as we go up in temperature. This is 30 degrees. This is now the higher pH, 3.7. There are the clusters. It gets messy. Clusters start to get bigger, but it's difficult to image. And then finally, we have nuclei that grow. Not only that, they coarsen over time. So this is after 25 minutes at 80 degrees, 67, 104 minutes. And so this case is one in which, or I should say that in the end, this is crystalline gibbsite. You can see the lattice in the second layer as well as the mica lattice underneath. Okay? It's a monolayer of crystalline gibbsite. Okay, so this is an example where I'm reluctant, a little reluctant to call it classical, but it's fairly classical description of this, except that it makes many, many nuclei, and then they coalesce over time to form a system in which the characteristic length scale is growing with time. So to summarize, I've shown you that nucleation, that the picture of Gibbs certainly is not incorrect, but the devil's in the details, and those details matter for a lot of systems. And the world is more complicated, I said, for two reasons. One, because of this increasing complexity of the free energy landscape, and the second one is because of the influence of dynamics. And I showed you a number of systems in which this is true, including classical nucleation in the gold system, the case of calcium carbonate where there are multiple phases available, the transient states being stuck in the amorphous state and making many, many nuclei that then coalesce. And with that, I want to thank the people who did the work. I've named the people who were responsible for most of this, although I can see that I neglected to mention Zhang Ma and Shui Zhang, who did the work on the organic polymers, on the peptoids. And I want to thank the funding agencies, particularly the Department of Energy, Basic Energy Sciences, and I want to thank you for your attention.
So now,
Jim, fantastic. So I was wondering how to explain the existence of polymorphs, whether using classical theory of nucleation or the non-conventional one. So some polymorphs can exist all together at the same time. What is your opinion about this?
Well, I'll go back to this to this picture. So, it's no problem for more than one polymorph to form. That doesn't mean more than one polymorph is absolutely stable, right? Yes, one is more stable, but how do you take a solid and transform it to the other polymorph? If these are very close in chemical potential, then the rate at which you're going to transfer atoms from one to the other is very, very slow. But the solid has to nucleate the new phase, and once you've made a solid, the mobility of the ions in atoms inside it is so low that the probability of that is negligible. In the case of hydrated phases, it becomes easier because there's water around, and that certainly gives the ions in the solid more mobility. But I see no problem forming more than one polymorph. If you drive the solution above two different polymorphs, they will both form in some percentages.
Exactly. What is interesting is when you have a phase transformation, moving from one polymorph to another disappearing one immediately. That is very interesting as well.
Yeah, so if there's a big enough difference between these levels, as soon as you form the more stable one, it drops the supersaturation of the environment, whether you're in a vapor phase or a liquid phase, and the other one disappears.
Thanks for the wonderful talk. I have a question and I would like to have your comments on those. So do you believe in existence of pre-nucleation clusters in metastable zone, or it's a contested topic?
Well, so pre-nucleation clusters is a bit of a loaded term, right?
Yes, it is.
There have to be clusters prior to nucleation, or you don't get any nucleation, right? But the term pre-nucleation clusters refers specifically, let's see if I can explain this. I took that part of this slide out, so it's a little harder for me to tell you this, but let me give it a try. The term pre-nucleation clusters refers to a case where these microscopic states are actually very, very deep. And in fact, in that model, these large clusters, and I guess I showed it to you in this. These large clusters, they're of nanometer scale, and they're there even in undersaturated conditions. Now, nobody's ever seen them, right? So the question is, are they really there? Certainly in the Gibbsite system I just showed you, I'm on the verge of saying, oh, look, there's a special size here. We've got a bunch of clusters that are way higher in their population than I would have expected. And as I said, no one will be surprised in silicate systems to find out that there are polymeric clusters. They know that already, and certainly in iron oxides as well.
Thanks.
Thanks for the fantastic talk. I have two questions primarily related to the techniques used for nucleation and growth. The first is the use of electron microscope and what the role of the electron beam could be in some of the process. And the second question is related to the AFM, the kinetics of the process versus, that is, dissolution and growth, for example, being much faster than the rate of scanning that you have in the AFM. So how could these affect the?
Yeah, so those are both problems. In the case of the in situ TEM, in some systems, so for example, all the studies that have been done on metals, gold, silver, nucleation is driven by the beam. The gold nucleation that I showed you, it's all beam induced. That solution's been sitting around for months. It's stable solution, but when you put it into the beam, you create hydrated electrons, they reduce gold ions, you make gold. Okay, no question about it. In some systems, you can, so what we found for the calcium carbonate system is that you have to stay in the range of less than 0.1 to, even 100 is a little bit too big, maybe 10 to 50 electrons per angstrom squared per second. And then you can do work where the effect of the beam is negligible. And what I mean by that is if you just block the beam, do the same experiment, but don't open the shutter. When you open the shutter, you'll find that the world looks the same as it did when you did the experiment with the shutter open. In some systems, it's a disaster. In iron oxides, even though you can be at low electron doses, everything dissolves. And the reason why is because that creates iron 2. Iron 2 adsorbs to the iron oxide, it exchanges with iron 3. The iron 3 goes out, gets hit by electron, turns into iron 2. So you've got this continual process of removing iron from the solids. We found a way to mitigate that by adding in a scavenger, but those are the tricks that you have to play. So absolutely, you got to figure out how to make sure that you've got something where the electron beam is not driving your process, or it's got to be useful to you in driving the process. For AFM, your question was about the rate. Clearly, if species are labile, they're coming and going quickly. We're not seeing them. They're going to appear as maybe a streak, where the tip just happened to hit something. No question about it. We're blind to things that are faster than the speed of the scan. What I can say is that that AFMs are faster now. The microscopy I showed you, that machine now runs at a frame per second. But even a frame per second is pretty slow.
Thanks very much.
Okay, just one very tiny questions because we are running out the time, so please.
Yeah, just to go back to the polymorphism you're saying about the populations. I study a system where they have very similar solubilities, very similar free energies, but almost in all solvents we study, we only ever crystallize the one polymorph.
Yeah.
And we also know that, as you say, we think we know that clusters appear in the undersaturated phase. So do you think that's all just being driven by the structuration of the clusters, like the link hypothesis, or?
Could well be, could be the clusters. So in this case, calcium phosphate, that species represents only 7% of the calcium in the solution. And yet that is the thing that drives nucleation. So I get it, right? That you can find that unit even in the final crystal. And apparently, so remember, free energy barriers aren't everything. We have to deal with kinetic barriers too. And if there's an easy pathway because the kinetic barrier is low and the supersaturation is high enough, you go to the less stable polymorph for that reason.
Thank you.
So let's thank the speaker again. is there somebody of the organizers committee or local organizer that must be something, I guess?
On behalf of LOC, this is my pleasant duty to give a small token of appreciation.
Thank you very much.
Yes.